Hi everyone, I'm Kashim, a last year PhD student at Columbia University. Today I'm gonna present our paper, NeuDep, Neural Binary Memory Dependence Analysis. Memory dependence analysis in executables is a process of determining whether two machine instructions in an executable can access the same memory location. As shown here, compiler has the freedom to use two different registers as indirect memory addressing to access the same memory location. And the task is to identify if two memory access instructions can still access the same memory address. Memory dependence analysis has many applications. For example, we often have to retrofit security defenses at the binary level, such as control flow integrity. The key question here is to mark whether one function can call the other functions when there is indirect calls. In such case, we need to identify whether an indirect function call can point to the address of some functions. As another example, we might want to diagnose a crash based on the core dump. Based on the crash site, we often need to perform backward taint analysis to trace back and identify the instructions that contribute to the crash. In such a case, we often have to determine whether two instructions are dependent when they access the memory. Otherwise, a conservative strategy is to treat all memory access instructions to be dependent, which will lead to overtaint problems. However, detecting memory dependencies at binary level is a very challenging task. This is because all source level data structures, variables, and arguments are lost and compiled down to untyped registers and memory accesses. The task gets exacerbated as the binary can be compiled by different compilers, optimizations, and obfuscations. The classic approach to this problem is based on value set analysis. It maintains a striated interval to represent the possible range of each variables and performs abstract interpretation to identify whether two memory accesses can possibly have overlapped intervals to indicate possible dependence. However, it is known to be imprecise due to the high over-approximation errors when merging branches and not scalable to real-world programs. For example, the public implementation of VSA in existing tools have shown timing out after 12 hours on most of the spec benchmark programs. More recent approaches show promises by using machine learning to learn memory access patterns. However, learning only on static code does not capture its actual semantics. Therefore, it has been shown often learning spurious shortcuts, lacking robustness. Moreover, the granularity of existing approaches also limit the precision of the technique. Consider the following example where two instructions marked blue are actually dependent but using different registers, and two instructions marked in red are not dependent but using the same register with different offset. The VSA will predict the two blue instructions not dependent by predicting instruction I2 access heap, as RAX is commonly used as a placeholder to store the memory allocated by calling functions such as malloc. And it predicts I7 as accessing stack, as RBP is often used to access stack base. This is a false negative. However, for red instructions which are not dependent, the VSA simply predicts them to be accessing global variables, just because they both use RIP, which is commonly used in position-independent code to access relative addresses for global variables. Such coarse granularity will lead to potential false positive, as it cannot distinguish between the addresses accessed in global regions. Our key insight is to teach the machine learning model to reason about dynamic value flows, where it follows the instructions by applying the knowledge of semantics of each instruction and compute what values can flow to certain registers and memory. For example, here, when performing value flow analysis on execution along one path, we might end up obtaining RAX to be 5. Then two instructions are accessing different memory addresses, thus the value from RBX does not flow to RDI. When analyzing the value flows along a different path, we might end up obtaining RAX to be 3. Then the first instruction writes to the same address that the second instruction will read from, and the value will flow from RBX to RDI. Our idea is to train the model on a large-scale number of programs along with these execution traces involving memory accesses to help the model learn the semantics of various memory accessing instructions and compose them to reason about their value flow behavior. In specific, using dynamic analysis, we sample the instructions I, their execution traces T, including data flow and control flow, and the memory layout of the code A, and apply masked language model on these modalities as a self-supervised pre-training task. While predicting masked OP code teaches the model to synthesize the instruction, predicting masked values in traces and memory addresses force the model to learn to interpret instructions and their effect on registers and memory contents. After pre-training, the model is fine-tuned to statically reason about the value flows based on its learned knowledge from pre-training across memory along multiple paths and predict the memory-dependent instruction pairs. The intuition is that the model will apply its learned knowledge for value flow analysis to infer the memory dependence. We represent the code address space during execution as an additional input aligned to the instructions. This helps the model stay aware of the instructions' order to their execution effect. Moreover, we observe that RIP relative addressing is frequently used to access global variables in position-independent code. Therefore, feeding addresses can help the model to learn the semantics of memory addressing. For example, consider the following instructions from a real-world program in core utils. 3 instructions use RIP with different offsets to access the same global variable stored at 9208. By encoding the addresses of each instruction, we help the model infer the value of RIP and thus assist reasoning of the memory dependencies. In order to learn the heterogeneous input modalities, we employ different input representations to capture their key attributes. For example, for the first modality, the program instructions, consider the following 2 instructions. We always use 3 feature sequences aligned together to represent the sequence of instructions. They are code sequence C, which encodes the tokenized assembly tokens, code position P, which encodes the instruction boundary of the variable length instructions and the relative positions within them, memory access indicator M, which is a sequence of annotation for each token to indicate whether they access memory. We can thus save the length of square bracket in code sequence, which indicates dereferencing. To encode execution traces, which is our second modality, we follow existing work by treating each numerics as a fixed length 8 bytes sequence. Consider the following example of instructions where their execution traces represent the state values of each token during execution, and assume we start from RAX equal to 0. For tokens without any value like add, we use 8 dummy tokens. For registers and constants, we use their actual values with 0 padded in the front. For instructions that should have values but do not have because they are not executed because of the control flow transfer, we use a special value of that is 256, which is out of the range of a regular byte to represent it. Here, push.di is not executed as the jump equal to instructions right before it has changed the control flow of the code. We encode the third modality, which is the code address layout, using similar strategy of trace encoding. Consider the following example. Each address is also encoded by fixed length 8 bytes, but here we omit showing the first 5 bytes here as they are all zeros. Tokens belong to the same instructions, share the same addresses. The incremented address reflects the length of previous instructions, As shown here, the next instruction has its address only incremented by 1, indicating push RBP only occupies 1 byte in x86 syntax. We develop a fusing module to learn the interaction between these modalities for the reasoning of value flows, memory dependence prediction, and other downstream reverse engineering tasks which either assist or benefit from memory dependence analysis. In particular, for the instruction modality, after embedding the 3 sequences, we sum their embeddings and let them go through a number of self-attention layers to learn how each instruction token depends on each other. We employ a shared weight 1D convolution network with highway connections to learn the numerical value representations of both trace and address. We then feed the trace and address value representation to the instruction encoding to augment the code representation with the value flow information. We make the fusing process also learnable by a gated network shown on the right. Finally, we let the fused code representation to go through an additional number of self-attention layers to learn cross-instruction value flows and obtain a value flow augmented code embeddings. Such embeddings will be used to pre-train, fine-tune, and further tune for various tasks. We collect extensive open-source popular software to evaluate NeuDep on binaries compiled by various compiler optimizations and obfuscations. Regarding the additional downstream reverse engineering tasks beyond binary memory dependence analysis, we consider 3 tasks, namely predicting memory access regions, predicting function signature such as function argument count and type, and matching indirect cause. We consider 3 baselines including Anger's VSA implementation, Ghidra, SVF, and Deep VSA. We run NeuDep and other baselines on our dataset, separated by the optimization and obfuscation flag. On average, NeuDep detects 1.5 times more dependencies while having 4.5 times fewer misses than the second best tool. When comparing the inference time, NeuDep is 3.5 times faster than Ghidra and orders of magnitude faster than Anger across different binaries. We also ablate our design choices. We find that, first, pre-training the model to learn general value flows significantly improves the model's precision. Second, we also find incorporating code addresses layout substantially decreases the missing rate. Please check our paper for the detailed description of other design choices not described here. On downstream reverse engineering tasks, such as predicting memory region, on average, NeuDep outperforms the second best tool, Palm Tree, by 6.9 in F1 scores. On predicting function signatures, NeuDep outperforms Eclavia by 12.6% in accuracy. Moreover, NeuDep remains robust when the optimization level is increased, but Eclavia's accuracy decreases when it's on higher optimization level. To match indirect cause, NeuDep outperforms Eclavia and TypeArmor, achieving 3.2 and 7 higher F1 scores, respectively. In summary, we developed NeuDep, a new binary memory dependence analysis tool that learns to first perform general value flow analysis before learning to predict memory dependencies. It is more accurate and scalable than existing state-of-the-art. We demonstrate learning general value flow is helpful to a broad range of tasks that either assist or benefit from memory dependence analysis. Thanks.